that this one is a set of n entry. So this one is collecting, this one is collecting all these brackets, okay? According to what we discussed, last time, 2 days ago. So this one is a set of n equations, okay, with respect to n unknown. Okay? So now what I do is the following. Sometimes, unfortunately for you, is quite known. By the way, the problem is written this way. That is the minimization of, within the bracket, of the function phi with respect to x. Okay? And then what follows the following. It's ST. ST stands for subject to. Subject to means is a condition, okay? So this, what I'm indicating now, is a so-called constraint. And now, these might be m constraints, okay? So these are m constraints. On variable x. Okay, variable x because it's nx. Okay, so these are constraints. I don't know. These constraints depend on the problem. Okay, I don't know. I want to minimize blah blah blah, subject to the fact that imagine that I want to minimize a cost function. Okay, or I want to reach the top of the mountain, which is a maximization rather than minimization. Okay. Which is like saying it's a minimum of minus the mountain, because if the mountain is this way, if I make a minus the mountain becomes negative, okay? So easy. Then if I say I want to maximize to go to find the tip of the mountain, subject to I need to go around the street. So all the trails, all the street, all the roads. So I need to find the maximum that I can reach constrained to. So I'm obliged to stay in the road. Okay? So perhaps the tip of the mountain. Okay, these are the contour lines. So the tip of the mountain is here, but if there is a road, and then there is another road here, and then there is another road there, okay? So that means that I'm constrained. Okay, perhaps to stay in all these roads, okay, which is impossible. But let's say I am constrained to stay in all the roads, which is, this one is g of x equals 0, and the other, forget about this, and this one is g of x equals 0. Okay, so these are two constraints. So what is the maximum of this function constraint that I need to stay in the road? Okay, the maximum is here. Because it's not there, because I cannot stay there, because I have all the set of constraints. So now, these are very typical. Now, the way to solve this kind of problem is by the so-called Lagrange multiplier method. Lagrange multiplier method says the following. If you have a set of constraints, like in this case, what you do, you create a new problem, which is, you create the Lagrangian function, which is this L function, where you put all the constraints into the function itself. So you take one by one, and you put there. So G1, G2, G3, blah, blah. Now, every one of that is multiplied by a scalar. Now, this scalar is something that I don't know. Okay? So the number of unknowns now are augmented. Augmented means increased by these constraints. And these constraints are called Lagrange multiplier. So now I need to solve a problem where the number of unknowns are n plus n. Okay? So in total, I increase the number of constraints, but I put the constraints into the equation that I need to optimize. So rather than writing in this way, which is quite annoying, we prefer to write everything in a compact way. And so since I want to write everything in a compact way, all the constraints is a vector, G. So it is lambda transpose times G, because I have lambda, vector of lambda multiplied by G. Now, what I need to optimize now is this Lagrangian function, this L. That, as I said, in this Lagrangian function depends on n unknown and n unknown. Okay? So the total number of unknowns has been augmented to n plus n. Okay? So if I need to find the minimization now, the minimization can be found by writing a set of equations, remember it's here, so a set of equations where I set the gradient with respect to the Lagrangian to 0. Now, the gradient of the Lagrangian with respect to the variable x set to 0, this is a set of n equations, because it's similar to that. Okay? And I can also, minimize, so compute the Lagrangian of compute the gradient of the Lagrangian with respect to the the Lagrangian parameter or the Lagrangian coefficient, and these are n. So in total now I have a set of n plus m equations into n plus n unknown. Now it might be easy, it might be complicated to solve. I mean, it depends on the case. Now, if you're not convinced that this trick works, I mean, now what you do, you simply make the following. If I compute the gradient of the Lagrangian with respect to the Lagrangian parameter, and you set to 0, it comes out of this equation. But this equation is exactly the equation in the top. Okay? So I didn't touch it. So the constraints are just here. Okay, the constraints remains there. So I simply need to solve another problem. Now, let's look, for instance, an example. Assume that I have a quadratic function, okay? And my constraints is very simple because it's linear. So my, the problem I'm now solving is the following. I have a quadratic form. Let me write here. I write here so it remains here. It's better. So I have my, my quadratic function. These are the axes. Of course, I draw in 2 dimensions because I cannot draw more. Huh? So, but this is, and my quadratic function can have all the contour line this way. Okay. So this is the contour representation of. Now I try this kind of ball, which is large in this way and a squeeze on the other. Okay. So I want to find, this is the minimum. But I want to find the minimization of the quadratic form subject to, look at that, subject to, C transpose X equal 1. Now what is this C transpose X equal 1? Oh, so let's write it. This is X1, this is X2, and then that one says C transpose X equals 1. So what is that? It is C1x1 plus C2x2 equal 1. What is this?
A line.
A line. Okay? So I want to find the minimum subject to that the solution stays along the line. I don't know, something like that. Okay? So, since the solution is to stay along the line, that's a constraint. Then I need to find the minimum along this line. Okay, so the line, is the one which is indicated here. Okay, and so the minimum, it's easy because the minimum is there. So which means that it's like if I take the quadratic function, okay, which is there. I'll try to sketch it, and I cut it, the quadratic function, which is cut it this way, and then resulting surface, okay, is like a cut in this way. And then I need to find the minimum for that, which is, move the part. Okay, clear? Huh? So, that's one possible, constraint, which is very easy. I would say the easiest one. Now we will see that, for instance, in array processing, these kind of constraints are very, very, very common. Array processing, what is array processing? Is every time you have a set of sensors, and you need to record you need to estimate some parameters of the field that is propagating over this array of sensors. One array of sensors that probably you have used is the one that is you play tennis with the screen, okay? And there is at the bottom in front of the TV, there is an array of sensors. These are acoustic on ultrasound. So what you hold in your hand, it seems is a tennis stick, but it's not a tennis stick. It's simply a transmitter, ultrasound transmitter. So when you make this kind of movement, the array, which is on the bottom of the TV, is estimating your position. By the way, it's similar to the homothermometry. Remember, I said the homothermometry is where you have a transmitter which is moving around you. You need to estimate where is the transmitter. So, which is similar, okay? So anyway, in that kind of application, you have a set of constraints, and you write a set of constraints which is similar to that. Now, so in this case, now let's write it together. So let's solve together the Lagrange multiplier method. So this is the Lagrangian, okay? So the Lagrangian now is a set of unknown, and then there is a 1, which is a scalar, okay? This is a scalar, so n is equal to 1. So I have in total n plus 1 equations. So what I need to do is the following, I write, the optimization, okay, is carried out in this way. I computed the gradient with respect to the unknown, set to 0. This means that this creates a relationship between the Lagrange multiplier and my objective function to minimize. I calculate x. This chain of relationship means, a set of, rules, a set of equations that you can solve. If you go to the book, you have by extension. Okay. So you have x equal to lambda 2 multiplied by something. Okay, and this something includes a constraint because it's c. C is the constraint. Okay. So lambda 2 is still unknown because I don't know lambda. So I need to find the lambda. So I plug these x there. I plug x, if you like, I plug these x into the constraint. Then I get my solution for lambda. I replug back again, so it's typical, when you have two equations to solve, you start a derivative with 1, you take, you get a partial solution, you move this partial solution into the first one, you compute the gradient with respect to the first, okay? So I would say, it's something that probably you have done in calculus analysis or something. Okay, so then at the end of the story, this is the optimum. So this is the minimum. So notice that the minimum depends on the constraint. And by the way, if you look at down here, it is C transpose A to the minus 1. So I need to take the matrix A, compute the inverse, and then, and then multiply by C transpose in C. Okay. Now, by the way, remember, the inverse is different. It's different for 1 over the matrix. 1 over the matrix has no sense. Never write this way. I think it's trivial, but So what is written there is C transpose A to the minus 1 C. Now I can write into the denominator because this one is a scalar now. Okay? Because I don't know, this one is 1 times n, this one is n times n, and this one is n times 1. Okay, so in total it's a scalar. Now, but you know, never write this way, 1 of A. Because this writing makes no sense. Okay? So if you want to lose the exam, write this, you know, you never pass the exam. Okay, clear? Because it makes no sense. So you should have studied this as again, you know, the first year course. Now, you know, I can be more involved. Okay, you know, I give you just a solution, but you know, I can be more, you know, fuzzy. I can write a quadratic form with many, you know, with a set of constraints. Like, I don't know, think about that this problem is a multidimensional. So when I set a constraint, this is a parabola in the hyperspace, which is called a hyperparabola, okay? And then I need to cut by hyperplane, many hyperplanes. Huh? And so at the end of the story, I can write m hyperplanes, okay? And by the way, m should be smaller than n. So if my dimension, like here, is 2, n equal 2, the m can be up to 1. So I can have up to 1 constraint, okay? So the number of constraints, you know, should be smaller than n, okay? In this case, it's 2 and then I put 1. Okay, so going back to the point, you know, in this case, if I have the n dimension, I can write a set of constraints, many constraints. Every constraint is a hyperplane. It's just an abstraction. So, and then I can write all the minimization. So you see, it's a minimization of a quadratic form. Now, in order to make it more general, I can write for a complex value. Okay. By the way, if you wanted to make it for the real, then you need to just write a transpose. Okay. So anyway, so you know, I have these minimization, the quadratic form in a complex domain, which is, you know, it's even double the number of unknown because I have n complex variable, which is 2n real variable. And then I have a set of constraints. Okay, so this is most general. Then what I do, you know, I need to take my constraints, rewrite into real and imaginary part, blah, 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 and so on, and then I solve it. When I solve it, you know, this is my solution. Okay, so this is the optimal point. This is the optimum, this quadratic form with a set of multiple constraints in a complex domain. So, I mean, you don't need to remember by memory this one. I don't remember myself, so I cannot ask you to remember something that I don't remember. Okay? So a professional way is that when you need it, you open the book. As someone was asking me how the oral is done. The oral is done because you have a book in front of you. Okay? So, because this is the way the engineer works in a professional life. They don't remember everything. Most of the case, you know, they know where to go to search for that information. And this is what I'm asking you. When you do the oral, you need to know where to search in the book for the information that I'm asking you, which is the question I'm asking. Okay? So this is the degree, you know, this is the further degree of maturity that I'm asking you. So, you know, as I said at the beginning, I want to shape you as a small engineer, which means, you know, to be as much professional as you can tell you. Now, this concludes, you know, what was left. Okay, so I move to the second part. Now, we kept working with problems that has to do with linear problems. Now, let me just refresh your memory. Okay, so this is chapter number 2. So, you know, what we have seen. We have seen so far that if you want to get rich, you know, at the end of the story, we need to solve a problem where we have a matrix, time a vector. You see, I'm not writing anything, because it depends on the problem. So I have a matrix, I have a vector. The vector is what I'm looking at. Is equal to another vector that is the data. This matrix, the matrix that I indicate there, depends on the problem. So according to the problem, this is a problem and model dependent. So if I'm making prediction, of the value of the stocks, then this matrix has a particular shape. If I'm doing something else, then that matrix has a different shape. So what we have seen about this problem here, okay, is that, for instance, if I have a matrix here, A, and then I have my unknown vector X, and what I need to get is my data that is B, this is the fitting that I'm going to do. So my goal is to get X, right? And what we did, I'm refreshing what we did, okay? And what we did, we tried to write, as a function of X, remember, X is the unknown. So I wrote the least square solution. And the least square was that, I take the error, that depends on X, the error vector, transpose, multiplied by error that depends on X. Okay? And I set this one by computed regression to 0. This is what I did. By writing bias 10, so by writing one piece by one, what I got is that this one is equal to X transpose, A transpose, A, X minus 2 times, it is B transpose A X plus B transpose B. And this was a quadratic form. So if I look at that, you look at a few pages back, this is the quadratic form. Okay? And by the way, we call this one R. We call this one P transpose. And we call this one probably called JZ. Okay? This is what we did. We minimize that, right? So the kind of problem that we need to solve is this one. So I told you, many times we have to solve a problem like that. AX equals B. B is the data, A depends on the model, and Tuesday we will see, just to make a concrete idea, very solid idea what the model is, we make a set of examples. Right now, for you, the only model we discussed together is just the model to make a prediction from a training set, okay? Using, a very easy data analytics example. But, we will see more later. So this is the context, okay? Now, I don't look at the second part because, before proposing any algorithm, I need to understand perfectly what AX equal B means. Okay? It's very easy, we need to look at that. So AX equal B. So the discussion now is, what is AX equal B? What does it mean? Now, let's look at it. So, the linear algebraic model gives a complex, powerful structure for signal modeling, which is that one. Okay? So, filtering and identification estimation can be modeled by a set of equations. Okay? And these are the equations that I need to find. And there's my unknown, which is X. Okay? So, which is, as I said, it's data, okay, model, unknown data. Okay, so just to remember. And usually, typically, V is noisy data. So there is a noise. So if in the data there is a noise might be modeled by some, stochastic parameters. So we need to get inside. So we need to understand how to describe the stochastic parameters that are hidden into V. But this is something that, since stochastics takes time, so you need to digest the matrix, and then next week, we slowly enter into the stochastic block. Okay? But I need to tell you why we need this stochastic model. And this is something that I started to tell you at the beginning next week. So I only tell you why, and then we start introducing the model. So A, as I said, accounts for the model, accounts of what we are doing. Okay? A, the matrix A. Now, let's see, in a different point of view, what does AX equal B means? Now, AX equal B means a transformation, linear transformation. Don't look at the figure now. What is, do this way. Otherwise, look at the figure. Okay? Here. So what is AX equal B? Now, AX, you know, the matrix A is composed by columns. And every column is a vector. With the size. Okay. So the matrix A at equal B, the matrix A is composed by, you know, a set of columns. A1, A2, okay? So these are all the entries that are ordered in column of the matrix A. A and N. Okay? So the length here is a set of n numbers, okay? And I have a vector, so a set of columns that compose the matrix A. Now, this is A. So when I multiply, and by the way, this includes the model, okay? So when I multiply this matrix with X, X1, X2, X, these are scalar, okay? So how do I calculate the product by, you know, by matrix time vector? So I take every row and then multiply by the column. Is it that? Right? So every entry. So A11 X1 plus A, you know, 1, 2, X2, blah, blah. Okay? And so on. Now I can rewrite in this way. This can be rewritten as A1 times X1 plus A2 vector times X2. Now, this, you know, this ordered set is a vector because, you know, it's a column of that matrix. So that one is, you know, is an m times 1 vector. Okay? That one is another m times 1, and so forth. Okay? Until the end. It's written there. I'm just pairing. Okay? So here I wrote in an extensive form so that you get to figure out that the matrix A, you see that matrix here, is a big matrix. So I mean, I take it in a column. And this is what you see, okay? So every column of that matrix is a set of n numbers, right? Okay, so what does it mean? It means that, you know, every column describes one point in the n-dimensional space. So imagine now, let's make it very easy. This is the table, okay? So imagine now that I have two vectors. Okay? So two vectors means, you know, in the case I'm illustrating now, is that m is equal to 3 and n is equal to 2. Okay? So I have m equals 3, n equals 3. Okay. Now, the one I'm describing, you know, I use the table. I will always use the table for that. Okay? So, now, I have the first vector. The first vector is A1, describe one vector, okay? Which is, you know, with respect to the origin, is a point. But this point is linked to the origin, then it's a vector. Then I have, you know, A2. What is A2? A2 is another vector, I don't know, it's this one. Okay, this is A2. So A1 and A2, they stay here, okay? So the only, how many do I have? I have just two, right? Okay, so in my problem that I'm describing now, I have these vectors that are three-dimensional, but you know, they stay in the plane. So the space that I'm describing is composed by three dimensions because I mean, every vector has three numbers. So let me write it. But I have two. So I have A1, 1, A2, 1, A3, 1. Okay, this is the vector A1. Then I have a second vector. I have A12, A22, A32. And this is the vector A2, right? So I have three numbers, and three numbers describe a three-dimensional space. So three numbers, if I say I have a point here, in order to describe these points, I need three numbers. Do you agree with that? Okay? So, since I'm dealing with three numbers, and I have two vectors, these two vectors stay in a plane. Or other words, that's because I draw here, but you know, so these two vectors describe the plane. So this is the plane, which is described by these two vectors. Okay? Now, what is the problem? The problem is the following. I have this multiplied by x1 plus this multiplied by x2 is equal to b1, b2, b3. Okay? Now, b1, b2, b3. Okay? So, here it is where it's b. Okay? So b is the data. This is the data. A1, A2 is the model. Okay? So, you know, what's happened here? It happens that, you know, the data is not contained into the plane described by the model. It has a component which comes outside. Now, so if, you know, this is my vector of the data, and the only that I can see is only the projection of the point onto this plane. Okay? So this is the projection of B onto the subspace described by A, because A is the matrix. Now let me tell you in a different way. Suppose that, you know, you are transmitting, you are listening to the radio. Okay? Now it's digital, but you know, let's make analogy. Okay? You are listening to the radio. Now the radio, you know, you decide that the radio, okay, you decide that your radio is within 100 megahertz. The bandwidth is, you know, 1 megahertz around 100 megahertz. Okay? That's your signal. You agree? This is, you know, this is the frequency axis. This is 100 megahertz. And this is the music. The width of the music is 1 megahertz. Okay? This is the music. Make it easy. Huh? Now, you know, my data, when I record, when I receive the data, I put a filter, and this filter is that big, right? Okay, so, you know, this component of the signal is signal, but the other, you know, which exists in that is what? No, noise, right? So, what is noise? Noise is everything which is not signal. So, let's say another way. If I have a vector here, by the way, you know, this is B. What I record here is B. What I get here is a B projected onto the data, onto the model. And the model is A, because I transmitted in 1 megahertz, and you are recording in 2 megahertz. So it's not because you are stupid, it's because, I don't know, the acquisition system has 2 megahertz bandwidth. And so you try to do what? You try to filter more. Okay, you filter more, right? Now, let's look in algebraic form of filtering.
Sorry, I don't get why B is different from BA or...
Yeah, oh, because let me sketch again. This is my signal and this is my 100 meg, okay? This is the real music, okay? So, but you know, for some reason, this is 1 meg. But for some reason, my receiver, my acquisition system, for instance, you know, has a filtering that, you know, is a band pass filtering that is, for instance, 2 megahertz. This is what I get, okay? So what I get is that this is information, and that's something else, okay? So this one contains noise, contains blah, 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 you see? Okay. So what I record, my data, is what comes out from this filter to megahertz. That's the data. So, I mean, the data is the information that I need to process. And the information that I need to process is the one that comes after 2 megahertz filter. Okay, now? So, what does it mean? It means now that everything that is inside here, all this information which is contained here, is the equivalent of B. Because it's all my data, which contains the true data and some noise. Okay? So, what is the data that I need? Is the one that is obtained by filtering in this way. Okay? So, and this one that I obtain by filtering is BA. Okay? Now, you know that there is noise also inside BA, which is inside the 1 megahertz. But you know, at least let me cut out everything that I know for sure that is noise. Clear? Okay. Now, what is in this case? Now, in this case, you know, this is B, the data. And this is A1 and A2. A1 and A2 is, you know, is the plane which is describing, now it's a plane, which is describing the model that, you know, is the signal that I transmitted, for instance, in this case. So what I need to do is the following. I need to take this vector and project into that. Which means I need to take this vector and compute about this vector the projection onto this substrate. And only this one makes sense. So if I have a vector here, this component is something that I cannot justify with my model. So it's a noise. It's something that I cannot observe with my model. So it's noise. So noise is everything that I cannot observe. Now, going back to this example, everything that is here is not really noise because, I mean, it's another station. So if I make a receiver that decodes, channel 1, channel 2, and channel 3, then, you know, I get 3 stations. So these are not noise in practice. These are other stations. So it's Radio Milano 1, Radio Milano 2, Radio Milano 3. But, you know, since my acquisition system is too large, too broad, then I collect, okay? I put into my system Radio Milano 1, Radio Milano 2, and Radio Milano 3. Then what I need to do is I need to cut out, filter, Radio Milano 1 and Radio Milano 3 because I want to keep Radio Milano 2. That's what I need to do. So, when I have A1, A2, A1, A2 belongs to the matrix A, and these are due to the model. So, since, as I said, the model is everything which is, the noise is everything which is not in the model. So, again, you know, A1 and A2 are describing this plane, but the data is here. So what I need to do, I need to take the data and project into this plane. I need to filter the data. So this algebraic operation, which is taking the data and projecting, is the algebraic equivalent of filtering, which is of course more evolved. Because, you know, if I ask you, take the stocks, Apple stocks data, and filter the data such that the data are cleaned up, everything which is not predictable, you don't know how to make it. Because you can just solve the least square problem. So, in this way, we know better, more, the structure of the problem itself. Now, this is what is written in this picture. Now you can read it. Now you can look at that. So, what's happened here is the following. I have A1 and A2, which is illustrated there. Okay. Now, A1 and A2, you know, they don't need to be orthogonal one another. Okay. But at least I describe the plane. So, this is the plane, which is this plane means that every time I have a measurement B, this one is the projection of the measurement where onto the subspace spanned by the vector A. Because x1 is a scalar. The only that describes this subspace is the A1 and A2. So this B is the projection of B onto the subspace of A. B is the data, okay, the noisy data. Projection of B onto okay, so how? Tell me.
Yeah, just you write B in Rm, just say Rm. In the text, just look at the picture, you see B is no element Rm. It should be Rm, I think.
No, that one is 2.
No,
Oh, okay.
In the text, just below.
Thanks. Thanks. Sorry. Surely it's wrong in the book because I just copy paste from the book. So one mistake. Thanks. So that's the point. So you know, I take B and I project into that subspace. Then you know, how do I call it subspace? Now that subspace is indicated by this character here. Okay. And this means that it's a range space of a matrix A. So is the subspace described by the column of the matrix A, which of course now it's only, you know, it's a very simple model because I have just, two vectors in that illustration. But in general, this subspace might have many more dimensions, okay? So by the way, sorry, I forgot. And you know, and what is that? That one, you know, is, which I can indicate as B vector minus BA, okay, is something that resembles a noise. Because it's something that I cannot justify with the model. Okay? So, you know, in other words, it's like it's like if A1 and A2 are describing this plane, and you are living because your model is constraining you to find solution within this plane. Okay? So, and you are living in this plane, So you are like a bug. Okay? What's a bug? Okay, so you are like a bug. And then you know you are constrained to stay in this plane. If you measure something, which is here, you don't see that component. That component for you is something that you don't want to see because you cannot justify it. Because you can only see everything that stays in the bug subspace, which is a long plane. Okay? So the third dimension is something that you don't see. And then this extends even more. For instance, for a bug, you know, the third dimension can be this, here, there. I mean, if you live in this plane, you know, everything that stays along this line, you know, does not exist for everything that has to stay in the plane. Now, once again, you know, my goal is not to understand, is not to solve the problem, is to understand the problem. Okay. So, at the end of the story, what are the solution of my equation Ax equal b? I cannot find the solution of any b, but you know, I need to take b and decompose into ba plus its orthogonal complement, which is that which stays perpendicular to BA. Okay. Then you know I cannot solve the equation with respect to BA perpendicular orthogonal. Okay. I can only solve the equation here with respect to BA. I cannot solve with respect to the other because the other is, let me say, something that is noise. You know, noise is something that I want to filter. So what I did, I filtered my observation, my data, with a model that you know is embedded into the matrix A. Now let's move forward. So a little bit more. So now what is the dimension? So we have a set of columns. So remember, you know, this one is n. So every one is n times 1. Okay. So I have a set of columns. Huh? So this one describes an n-dimensional space. Okay. So I indicate, you know, the range space with this calligraphic R. So the range space of matrix I, or A, is included or equal to the space which is due to this n-dimensional vector. Okay, so this one is a subspace. So this is a subspace, you know. So I can evaluate what is the dimension. Now, dimension of this calligraphic R, so the range space of matrix A, okay, which is the dimension of that space, is equal to R. And this R is smaller or equal to 1. Now, the rank of a matrix, rank, is the number of independent columns. Why do I say independent column? Because, you know, if in this plane there is another column which is obtained by linear combination, that is not independent. So my goal is to describe this plane. And so if I take one vector and then I take another vector which is a line, two vectors aligned, they're not describing a plane. Okay? So they're, I mean, it's the same. Okay? So what I say is the following. The rank of a matrix is which is the dimension of the subspace. Those two quantities, the rank and the dimension, coincide. So the rank is telling how many, you know, independent columns exist. And then this one is obtained by the dimension of the subspace. Now you remember that I was telling you that if I have a matrix which is symmetric, I can decompose into rank 1 matrices we saw by MATLAB. Okay, those one. And I said that one is a rank 1. And why is a rank 1? Yeah, because I have one column. It's one column multiplied by another row vector, but that is one column. And so since that one is one column, that is a rank 1, because I mean that is one vector. And any other column are just a linear combination of the first, because it's just multiplied by a scalar. Okay? So that is the case. Remember, I put you for you, you know. No, let me write this way. We call rank 1 matrix, which is Q, okay, and Q transpose. Or in general, Qi, Qj. In general, you know, the product of a vector multiplied by a column vector multiplied by a row vector, you know, it's a rank 1 matrix as a result. Okay? and that is outer product. Okay. So let's continue a little bit. So the rank of a matrix A is smaller or equal to the dimension of the column and row. Okay, that's another property. Now, a full rank matrix is full rank in the following case. If it is a square matrix, and then that means that the full rank means that the matrix is not singular. We know by algebra that if a matrix is singular, not to be singular, the column should not be linearly dependent on one another. Okay, which is another way to say the same words. If the matrix is tall and skinny, what is a matrix tall and skinny? Okay. This, let me sketch here. This is a tall and skinny matrix. If this, okay. And a fat matrix is a matrix where all the column here. Okay. This is the fat matrix. This is the tall matrix, tall and skinny. Okay, sometimes you just say tall. Okay, so you say, do you have a tall matrix? Do you have a fat matrix? Okay, which means long matrix or large. And then, full rank means that, in this case, all columns are independent, and for fat matrix, all rows are independent. So this one. Now we need to see the solution. Okay, what are the solutions we want to see? This is collecting exactly what we say. In case B belongs to the subspace, to the rank, or the span of matrix A, which is the subspace of the column of matrix A, this linear system has at least one solution. It is a coefficient of the columns that is necessary to have B, which is another way to say the equation. In general, it's possible to decompose B equal BA and BA orthogonal. Okay? Where BA belongs to the range space, which is the space of the column. And B orthogonal belongs to the complementary space, which is the null space. Okay? That is, N stands for a null space. There is a definition, so you can see it. So, now, if I want to solve the problem AX equal B, then what I need to do is that I need to take the projection matrix. What is a projection matrix? It's the one that takes a B and project into the space of A. That is a projection matrix. So, what does the projection matrix? It takes vector B and projected it. Okay, so it's a linear operation which is going this way. And we saw, even by MATLAB testing, that the projection matrix has some very special properties where the eigenvalues are 0, 1. Remember? Okay. Now, so what about if I want to get this one? So if I want to get this one, I can get the complementary, which is I take B minus BA. So when I plug in, I get the projector onto the complementary space. So what is this? I extracted the noise. So in case the noise is something that I want, I can just multiply by PA complementary. And then I get the noise. Now, perhaps, imagine here. I have 3 radios, rather than 1, 2, and 3. My interest is to decode number 2. Well, for instance, in my receiver, I want to receive number 1 and number 3. So I can make one projector, one projector, one projector. Or I make one projector, remove, and then what is left is this 2. And then perhaps I can do a bandpass filter, which is extracting this signal and the other signal, for instance. Okay. So if I want to extract the noise, which might be useful, then I use